Welcome back to my channel. Today we are looking at LC circuits. An LC circuit is a circuit which consists of an inductor and a capacitor. Joining me in today's presentation is Giselle the Gazelle. Thank you very much. Isn't she incredible? Thank you. Also joining me today is a new friend. This is Isabel. Isabel is Giselle's bestie. And being Giselle's bestie, she's heard a lot about this channel, and she wanted to join us in one of our presentations. So I'm really glad to have her aboard for this presentation. Please welcome Isabel to our channel. Thank you very much. This afternoon, the three of us built the circuit shown here. We have two D-cell batteries connected in series. They're connected to a switch, a single-pole double-throw switch. One end of the switch is connected to a capacitor, 22 microfarads. And the other end of the switch is connected to an inductor, or a solenoid, which acts as the inductor in our circuit. Oh, Giselle, sorry. I'm sorry about that. I knocked down Giselle. Sorry. You all right? Okay, good. Now, our switch has two positions. If I move the switch here to the right, I connect the capacitor to the batteries. And if I move the switch to the left, I connect the capacitor to the solenoid. In this experiment, we want to measure the potential difference across the capacitor as a function of time when the switch is in those two positions. To do that, we have connected a voltage probe across the capacitor. The probe is connected to a LabQuest, which is connected to the computer. Before we begin measurements, let's look at the theory of this circuit and try to predict what the voltage across the capacitor will be when the switch is in those two positions. At the beginning of the experiment, the capacitor is fully uncharged. Then the switch is moved to the right to position 1, connecting it to the batteries. When this happens, current starts to flow. It flows from the positive terminal of the battery through the capacitor to the negative terminal of the battery. This causes charge to accumulate on the plates of the capacitor. The lower plate becomes positively charged, plus Q, and the upper plate becomes negatively charged, negative Q. Eventually, current stops flowing when the voltage across the capacitor equals the EMF of the batteries. Here is a plot of capacitor voltage versus time. At the beginning, when t is 0, the voltage across the capacitor is 0. As current flows and charge accumulates, the voltage increases until it reaches a maximum value, which is equal to the EMF of the batteries. In our experiment, that final potential difference across the capacitor was equal to 2.80 volts. After the capacitor is fully charged, which takes less than a second for our experiment, we disconnect the capacitor from the battery, as shown here. But we have not yet connected it to the inductor. At this point, we still have a voltage of 2.80 volts across the capacitor, and we have the same charge of plus Q and minus Q on the plates of the capacitor. Then we move the switch to the left, to position 2, connecting the capacitor to the inductor. This forms the LC circuit. Now charge is going to start to flow. So current starts at 0, and then it flows as shown here. It flows from the positive terminal of the capacitor to the negative terminal. It starts at 0 and increases. The inductor tries to prevent that increase in current. So it acts as an EMF. And the lower part of the inductor is a positive voltage, and the higher is a negative voltage. So this EMF in this direction will oppose the increasing current up through the inductor. It is important to realize that dq by dt is less than 0 because the capacitor is losing charge. Also, this current is a positive number. So when we write the current expression, we should write it as negative dq by dt. So negative times a negative is a positive. So writing I as negative dq by dt will ensure that we have a positive value of the current, as shown here. Let's apply Kirchhoff's loop rule to this circuit. Let's start here at the capacitor and just form a loop that goes around like this. So first thing that happens is an increase in potential through the capacitor, so Vc, and then when it goes through the inductor, there's a decrease in potential. So we have minus VL, and that equals 0. So Vc is Q over C, and VL is L di by dt. And we'll put in what I is, negative dq by dt. We get this. And so we finally get for VL, negative L d2q by dt squared. So we want to put these two findings into our expression for Kirchhoff's loop rule. So let's take our Vc here and put it into the equation. And we will take our VL and put that into the equation. And this is what we get. Q over C plus L d2q by dt squared equals 0. Let's divide by L and switch the two terms. This is what we get. d2q by dt squared plus 1 over LCq equals 0. Have you seen this expression before? I think you have. This is the harmonic oscillator equation. This is the equation that describes simple harmonic motion. Here's our equation. Let's rewrite it like this. We'll replace 1 over LC with omega squared. This is the standard form that we usually see this equation. And we know what the solutions are. In this case, omega is the angular frequency measured in radians per second. So the three solutions we could write like this: A sine omega t plus phi, or A cos omega t plus phi. In these two solutions, A and phi are constants. Or we could write it like this: A sine omega t plus B cos omega t. These are all solutions for this equation. And in these solutions, A, B, and phi are constants. Because, and note that there are two constants in each of the solutions. Why is that? This is a second order differential equation. We have two derivatives here. To solve this equation, we have to integrate twice. And each time you integrate, you get another constant. So we have two constants here. Let's verify that this A cos omega t plus phi is a solution of our differential equation. So first, differentiate Q. We get this. Derivative of cosine is negative sine. So we have negative sine. When we differentiate this, we have to use a chain rule. Differentiate with respect to omega t plus phi, giving us sine omega t plus phi, and then differentiate omega t plus phi with respect to t. That gives us an omega in front. So dq by dt is negative a omega sine omega t plus phi. Now let's differentiate it again. Derivative of sine is cosine. Again, we get the factor omega coming in front. So we have negative a omega squared cosine omega t plus phi. Let's substitute these two expressions, so this one, into our equation right here. And we'll put expression for Q
put it right here. And our equation becomes this. First term, negative a omega squared cos omega t plus phi, plus omega squared times a cos omega t plus phi. Well, these two terms are the same, but they have opposite signs. So they add to 0. So we have verified that that indeed is the solution of the differential equation. What's that? Oh, Isabel doesn't want to just verify the solution. She wants to actually start with this differential equation and prove that this is the solution. That is something which we could do, Isabel, but I think it's a little bit too advanced for this presentation. There's something you need to realize about Isabel. Isabel is in high school, but she has already completed Calc 3 and is now taking differential equations. So she knows a lot more than other students. So I'll tell you what, Isabel, let's do that in another presentation, and you can be the star of that presentation. Is that okay with you? Great! Let's continue with our presentation. The determination of the constants. We have two constants in our solution, a and phi. So q equals a cos omega t plus phi. We need to find those two constants. How do we do it? We need two conditions to get those two constants. Well, these are called initial conditions. So first initial condition, when t equals 0, Q is the initial charge on the capacitor plates, which is given by C times the initial voltage across the capacitor, which was the EMF of the batteries. So at t equals 0, Q equals CE. That's one condition. Second condition, when t equals 0, I equals 0. Let's look at the second condition first. So I is negative dq by dt. Let's differentiate this expression. And we get the following. Derivative of cosine is sine. Again, we get the factor omega coming in front. So a omega sine omega t plus phi for the current. I'm sorry, derivative of cosine is negative sine. So the two negatives cancel out, giving us a omega sine omega t plus phi. At t equals 0, we know that this current is 0, and put t equals 0 into this expression, we get a omega sine phi. So the solution is phi equals 0, because sine of 0 is 0. Now let's look at the first condition. At t equals 0, q is a cos 0. So when t equals 0, omega t is going to be 0, and we already know that phi is 0, so q is a cos 0 when t equals 0. And when t equals 0, q must be CE. So a cos 0 equals CE, and cos 0 is 1, so a equals CE. So our solution becomes, with the constants correctly determined, q equals CE cos omega t. Frequency and period. In the solution, q equals CE cos omega t, the angular frequency in radians per second is omega equals 1 over square root LC. The frequency in cycles per second, or hertz, is F equals omega over 2 pi. We know this because omega equals 2 pi F. And so therefore, F is omega over 2 pi. And when we put in what omega is, we get the following. F is 1 over 2 pi square root LC. The period, which is seconds per cycle, or seconds, which is the time for one oscillation, is 1 over F. So we just take 1 over 2 pi square root LC, and we get T is 2 pi square root LC. Look at this expression. If we know the capacitance and we measure the period of oscillation, then we can find the inductance. I know that what the capacitance of our capacitor was. It's written right on the capacitor, 22 microfarads. But I don't know what the inductance of that solenoid is. But we can determine it by measuring the period. And that's what we're going to do later on in this presentation. Graphs of charge and current. Q is CE cos omega t, where omega is 1 over square root LC, t is 2 pi square root LC. Here's a graph of the charge on the capacitor versus time. It is a cosine graph. It is a maximum when t equals 0. It has an equilibrium of 0, and it goes between negative CE and CE. And from 0 to t, period, we have one cycle, another cycle from t to 2t, and another cycle from 2t to 3t. And it keeps going on. The current is negative dq by dt. So let's differentiate our Q to find the current. So we have the factor CE in front, a constant. Derivative of cosine is negative sine, so we have the negative and then the sine. And when we differentiate cosine omega t, we get a factor omega coming in front. So we get this. And putting in what omega is, 1 over square root LC, we get this in the end. I is E square root C over L times sine omega t. So it is a sine function. When t is 0, the current is 0, and it goes from negative square root C over L to positive square root E times square root C over L. So negative E square root C over L up to E square root C over L. And it oscillates between these two. From 0 to t is one period. And then t to 2t is another period, and 2t to 3t is another period. And it keeps going on. Energy in an LC circuit. There's potential energy in the LC circuit. The capacitor has potential energy. UC equals Q squared over 2C. This is the energy associated with the electric field in the capacitor. Then the inductor also has potential energy. UL is a half Li squared. This is the energy associated with the magnetic field in the inductor. Here's a graph of charge and current on the same axes. What I want you to note here is when charge in red is the maximum or minimum, so when charge has the maximum magnitude, the current in blue is 0. So here, maximum magnitude charge, 0 current. Here, maximum magnitude charge, 0 current. When Q has a maximum magnitude, I is 0. Also, when I has a maximum magnitude, such as here, the charge is 0. Or maximum magnitude here, for charge, for current, the charge is 0. So when I has maximum magnitude, Q is 0. So when Q is maximum, all the energy is going to be potential energy in the capacitor, and potential energy in the inductor will be 0. And so the energy is going to be transformed between all potential energy in the capacitor to all potential energy in the inductor and vice versa. So it goes from capacitor to inductor, back to capacitor, then back to the inductor, and so on. Let's find the total energy in an LC circuit. Total energy is UC plus UL, given by these two expressions. Let's substitute in our Q and our I. So total energy, so the first term in red is Q squared over 2C. We just squared this term, divide by 2C, we get this. The second term in blue comes from the inductor. 1/2 L, right here, times I squared. E squared C over L sine squared omega t. Notice, in front of these terms, this is 1/2 CE squared. This is also 1/2 CE squared. So we have a common factor of 1/2 CE squared. Let's take that out. And then we multiply that by cos squared omega t plus sine squared omega t. Well, I hope you remember that cos squared omega t plus sine squared omega t is equal to 1. And so our expression for the total energy is 1/2 CE squared. And that is a constant during these oscillations. Total energy is a constant, equal to 1/2 CE squared. Energy is transferred back and forth between potential energy in the capacitor and potential energy in the inductor. Let's look at the voltage in the LC circuit. The voltage across the capacitor is equal to the voltage across the inductor. That's clear. The inductor and capacitor are connected together, so they must have the same voltage across them. So VC equals VL. There are two methods to calculate the potential difference. First of all, we could calculate it from the capacitor, Q over C. Put in our Q, CE cos omega t, divide by C, and we get E cos omega t. Or we could calculate it from the inductor. VL is L di by dt. So L d by dt of this is I, so differentiate this. Derivative of sine is cosine, and we'll get a factor omega coming in front. So we get this, L e omega square root c over L cos omega t. Put in what omega is, 1 over square root LC. And we get this, E cos omega t, which is what we expected. So VC and VL are equal. So the voltage is E cos omega t. Let's look at a graph of potential difference versus time. So there's our potential difference. It's a cosine. There's omega, there's t. And so this is what we get. A cosine function. Equilibrium is 0. It goes between negative e to positive e. And we have one cycle from 0 to t, another cycle from t to 2t, and then another cycle from 2t to 3t. So this is what we expect the potential difference across the capacitors to be in our experiment. Let's see if that is what we get.
We are now ready to begin our measurements. The first step is to make sure that the capacitor is fully discharged. To do that, I will connect it to the solenoid. It is now fully discharged, and I will zero the voltage probe at this time. The voltage probe is now zeroed. Now, to make the measurements, I'm going to have Giselle operate the switch. Is that okay, Giselle? Great. And we will have Isabel press the button on the mouse to start the data collection. Is that okay with you, Isabel? Thank you very much. Okay. First step is to charge the capacitor by connecting it to the battery. Okay, Giselle. Please connect the capacitor to the battery. Great. Now the capacitor is connected to the battery, and we are reading 2.80 volts on the capacitor. Okay, Giselle, can you please disconnect the capacitor from the battery, but don't yet connect it to the inductor? Great. Now we still have 2.80 volts on the capacitor. Okay, Giselle, I'm sorry. Okay, Isabel, can you please press the button on the mouse to start the data collection? Thank you. The data is ready to be collected. Now, Giselle, please close the switch. Connect the capacitor to the solenoid. Okay, the data is being collected. We are collecting 20,000 samples per second for 3 seconds.
Here's a measurement of the capacitor potential difference as a function of time for the 3-second experiment from 0 to 3 seconds. Here's what we get. At the beginning, it's constant, 2.8 volts. Then we have a sudden change, and then it's constant at 0. I don't see any oscillations here. I see a sudden spike, and then it becomes 0. Let's look up close in this region. Maybe something's going on there. Now we've got from 1.847 to 1.867 seconds. We're looking at a time of 0.02 seconds. Here's what we get. Whoa! Now we see oscillations. But they rapidly go to zero. So we have oscillations here, but the amplitude is decreasing with time. Why do you think the amplitude is decreasing with time? Take a moment to make a prediction, or to give a reason why the amplitude decreases with time. Okay, you've had some time to think about it. Let's look at why it decreases with time. There is resistance in the wires and the solenoid, which converts potential energy into thermal energy, lowering the total energy of the system. This is not just an LC circuit. This is really an RLC circuit, and that resistance is taking energy out of this circuit. Here's a very important and exciting question. Can we measure the inductance of the solenoid? The answer is yes. We can use this expression. T is 2 pi square root LC. If we know C and we measure T, we can find out what L is. From this expression, just rearrange, we get this. L is T squared over 4 pi squared C. So we know what C is. It was 22 microfarads. Here's our graph of potential difference versus time. Starting right here. 1 cycle, 2 cycles, 3 cycles. 3 oscillations, so that length of time is 3 periods. So 3t was 0.007573 seconds. Divide by 3 to get the period. And we get this, 0.002524 seconds for the period. Now, substitute everything into this expression to find L. Period squared divided by 4 pi squared, 22 times 10 to the negative 6. We get 7.33 millihenries.
In our next experiment, we want to determine the effect of adding iron bars to the solenoid. So I'm going to stick these 5 iron bars into the solenoid, like this. Now I want you to make a prediction. What do you think will happen to the inductance when I put the iron bars in the solenoid? Spend a few moments to make your prediction.
When iron bars are added to the solenoid, what happens to the inductance? Let's look at the definition of inductance. It is a ratio of magnetic flux to current. Magnetic flux over current. When iron bars are put in a solenoid, the magnetic field in the solenoid will magnetize the iron bars, causing the iron bars to emit a magnetic field, increasing the total magnetic field inside and therefore increasing the magnetic flux. So for a given current I, we increase phi, causing L to increase. So when iron bars are added to the solenoid, we should increase the inductance. Here's a measurement of potential difference across the capacitor versus time for 2 cases. In red is a case where there were no iron bars in the solenoid, and blue is a case where there were 5 iron bars in the solenoid. What do you see about the periods here? With no iron bars, this is the period from here to here. And with iron bars, the period is from here to here. You will note that the period has increased when iron bars are added to the solenoid. That makes sense, because if we increase L, we should increase the period. Let's start here and go 1 cycle, 2 cycles over to here. So that's 2 oscillations. So this time interval should be 2 times the period. So 2 times the period is 0.008020 seconds. Divide by 2 to get the period. And we get the period here. 0.004010 seconds with 5 iron bars in the solenoid. Compare this where we had no iron bars in the solenoid. 0.002524 seconds. So we definitely increased the period when we added iron bars to the solenoid, and that increase in period came about because we increased the inductance. We calculate inductance from this expression. L equals T squared over 4 pi squared C. Here's what we found. With no iron bars, L was 7.33 millihenries. With 5 iron bars, it was 18.5 millihenries. Here's a summary of what we talked about today. First of all, in an LC circuit, the charge on the capacitor follows the simple harmonic motion oscillator differential equation. d2q by dt squared plus 1 over LCQ equals 0. The solutions for current, charge, and voltage oscillate sinusoidally with a period given by t equals 2 pi square root LC. Measurements of a real LC circuit show that the amplitude of oscillation decreases with time because of energy losses due to resistance in the circuit. The inductance can be determined by measuring the period of the oscillation using this equation. L is T squared over 4 pi squared C. So if we know C, we can measure T and determine what the L is. And when we add iron bars to the solenoid, we increase the inductance and the period. Thank you very much for your attention in this presentation. Giselle, Isabel, and I really appreciate your viewing of these presentations, and we hope you come back again. Please be sure to like and subscribe. See you next time. Bye.